In this video, we're going to take a look at alternating series and the alternating series convergence test. So first, recall that the infinite series 1 over n is the divergent harmonic series. And writing this series out term by term, it becomes 1 plus 1/2 plus 1/3 plus 1/4, and so on, all the way up to 1 over n, plus every term that we could possibly have out to an infinite number of terms. This was a series we know to be divergent, both from the p-series as well as from the integral test. So what we're going to do is modify that series slightly and ask, does the infinite series -1 to the n minus 1 times 1 over n converge or diverge? And so the big difference in this series is that -1 raised to a power that is not n itself, that differs by 1, will cause all the even terms to be negative. So we'll get 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, and so on, alternating the signs in between each term. And this is what's known as an alternating series. Now with this particular series, one thing we can do to look at the convergence or divergence is to pair up the terms following the first one, following that number 1. If we do that, the -1/2 plus 1/3 would be -1/6. The -1/4 plus 1/5 would be -1/20, and every pair of terms we get from here on out will always take a little bit more off that starting value of 1. But those fractions, they're going to approach 0 very quickly. So this sum starts from 1, keeps decreasing, and the terms approach 0. And so this will be a series that will converge. We're not going to subtract enough to go below 1 and keep going to -infinity, but we are going to keep subtracting until we reach a finite sum. And the alternating signs have turned what was a divergent series, the harmonic series, into a convergent series. And this alternating property is what we're going to look at with the rest of this lesson. So the first step is to formally define what an alternating series is, and also define the convergence test that goes with it. So an alternating series has either negative odd terms, so the first term, third term, so on. If we write it out as the series from n equals 1 to infinity for -1 to the n power times whatever sequence makes up this series. Or it has negative even terms if we take that same series and raise -1 to either the n minus 1 or the n plus 1 and multiply that by the terms of our sequence. That would cause the second term, fourth term, and so on, like we saw in the example above, to become negative. And the alternating series convergence test says that alternating series will converge if, first of all, the limit as n approaches infinity for the absolute value of the terms in that sequence approach 0, so the absolute value of the series passes the nth term test, and if a sub n plus 1 is less than a sub n for all values of n. And that's just a way to say that the terms in this series must be decreasing. If both of those conditions are met, an alternating series will converge. So we'll take a look at that through this following example. Determine the convergence or divergence of the infinite series from 1 to infinity, defined by -1 to the n plus 1 times n over 2n plus 1. And how we'll take a look at this, and a good idea for any series you're unfamiliar with, is to expand out the terms. This alternating series has even terms as negative, and it can be expressed as 1/3 minus 2/5 plus 3/7 minus 4/9, and so on. And so the absolute value of the terms is increasing. every term disregarding the negative sign is bigger than the one before it. Also, the limit as n goes to infinity for the absolute value of the series, which would be n over 2n plus 1, equals 1/2 and does not equal 0. Both of those are signs that we have a divergent series. The limit on its own would have been enough thanks to the nth term test, but this one breaks both criteria. So let's follow up with another example. The infinite series, starting from n equals 0 to infinity, for negative 1 to the n over 2n factorial. And again, we'll expand this out. This is another one that because of having a starting value of 0, will have even terms being negative. So our first term will be 1, minus 1 over 2 factorial, which is 2, plus 1 over 2 times 2, or 4 factorial, which is 24, minus 1 over 2 times 3, or 6 factorial, which is 1 over 720. And this will keep going. And notice those denominators are getting big in a hurry because of that factorial. The absolute value of the terms in this series are decreasing. So we passed one of the two criteria for the alternating series test. And the limit as n approaches infinity for the absolute value of this series, which is 1 over 2n factorial, will equal 0. That factorial grows way faster than the constant 1 on top. And so this series, we say, will converge by the alternating series test. Proper way to write out the explanation and proper conclusion. And the last thing we'll do in this lesson is to define the difference between two new terms, which are absolute versus conditional convergence. We can say that a series has absolute convergence if both the series of its terms and the series made up of the absolute value of its terms converge. So both the alternating series and the series where we force all terms to be positive, both of those converge. And a series has conditional convergence if the series itself converges, but the series made up of the absolute value of its terms diverges. And I'll finish by showing an example of both. So in example 1, let's go back to where we started. The infinite series from 1 to infinity, defined by negative 1 to the n plus 1 over n, which again is 1 minus 1/2 plus 1/3 minus 1/4, what we can now call the alternating harmonic series. The terms in the series are decreasing for all n greater than or equal to 1 if we ignore the negative signs. And the limit as n approaches infinity for the absolute value of this series, so the absolute value of this negative 1 to the n plus 1 over n, will be equal to the limit as n approaches infinity for 1 over n. We can ignore the possibility of having a negative 1, and that limit will equal 0. So this series does converge by that new alternating series test. But if we want to decide if it converges absolutely or conditionally, we have to look at the series made up of the absolute value of those terms, which in this case would be the infinite series from 1 to infinity for 1 over n, which we know is divergent because that is the harmonic series. So the alternating series converges, but the absolute value of the series diverges. Therefore, we say that the series converges conditionally. We must have the alternating series in order to have convergence. That's the condition that we need to meet. In example 2, the series from n equals 1 to infinity for negative 1 to the n plus 1 over n squared, this would be the series defined as 1 minus 1/4 plus 1/9 minus 1/16, and so on. First condition to note, these terms are decreasing. That denominator is increasing while the numerator stays the same. and the limit as n approaches infinity for the absolute value of this series, so the absolute value of negative 1 to the n plus 1 over n squared, will be equal to the limit as n approaches infinity for 1 over n squared, which is 0. So this series, just like in example 1, converges by the alternating series test. The big difference is going to be looking at conditional versus absolute convergence. The series made up of the absolute value of this alternating series will be the series from 1 to infinity for 1 over n squared, which converges because it is a p-series with a p-value greater than 1. So since both the alternating series and the absolute value of the series converge, we can say that this alternating series converges absolutely. Literally, both the series and its absolute value are convergent. And that's all for this lesson on the alternating series test and the definition of absolute versus conditional convergence. Thank you for watching.